Yeah, so very good evening to all of you. Uh, so hope you are doing well with the course, and we'll today do our penultimate problem solving session, and probably today we'll take up uh, some of the questions out of the previous week's content, and just discuss some concepts and related problems out of the current week content. Okay? So today actually we'll be discussing your laser beam machining, electron beam machining process, and then we'll discuss the basics of additive manufacturing (AN). Okay. Uh, so right now we'll start with the assignment questions from the last week content. I will share my screen for that. So yeah, this really is your some questions out of the last week's content, and probably all of you have been comfortable in answering these questions. So the first question was regarding the removal rate, volumetric metal removal rate in ECM process, and obviously this will correspond to your anode because the material is made your anode, the workpiece material is made your anode, and the cathode is actually your tool in case of ECM process, right? So yeah, that automatically discards option number. So no, sorry. So every option was related to anode only. Now, of course, the proportional is directly proportional to the density of the anode, okay? And then the removal rate is obviously volumetric removal rate. Okay, so current is, if you look at option number C, then if you take the first blank as current, then current is not inversely proportional to the density, rather it is directly proportional. Okay, so other than that, the first option is density of anode directly proportional to current. So that is also wrong. And the only correct option then becomes a volumetric removal rate is directly proportional to the density of anode in ECM process, right? So the second question was, which of the following cannot be used for producing code surfaces and impressions? Okay, now with USM, you can't really develop curved surfaces, and neither with ECM. Okay, actually, you can go with LBM process for that kind of applications. So option D becomes your correct option in that case. Okay. So this clear to you? So Third question was, why is the electrolyte flow necessary? We have discussed that in details the last session. Electrolyte flow is necessary, of course, to avoid deposition on the tool, to take away the excess heat, that is, to avoid overheating and precipitation. So both A and B are correct options in that case. Now, the next question was a numerical out of material removal rate in the same process. There are standard formulas. If you look at for the MRR in terms of centimeter cubes per minute, okay, you just plug in the values of your atomic weight, then current value, then density, valency, and Coulomb's number, okay, or Faraday's constant C, okay, which is 96500 coulombs. You just plug in the values and find out the MRR as 16.74 centimeter cubes per minute. Okay? And then the next question was, for using ECM process, the primary condition is, so of course the workpiece must be conductive, otherwise there you can't complete the circuit and the process cannot actually take place. Okay? Now, next question was if, okay, so this was related to your equilibrium gap. So this question was also derived, this equation, the parabolic variation of the equilibrium gap. This thing was derived in the last class. So you can directly say that if you have followed that class, that if PD is 0 in ECM and then the gap Y okay, increases by this parabolic function y naught square plus twice of lambda t whole to the power half. Okay, when lambda and t are the constant, lambda is the constant and t is the time, and y naught is the initial gap. Okay, so given that your electrode double layer is generated when actually the double layer is generated in proximity to an electrode, right? When it is dipped in an electrolyte solution, okay? At the interface of both, we find the electrode double layer being generated. So option C is the correct one for question number 7. Okay, I hope I got it. And then what are the various types of over voltages used in ECM? Yeah, so there is a nice curve explaining these over voltages during the process of ECM. Starting with activation, polarization, then ohmic and concentration gradient. Okay, these three are the different over voltages, and there is a nice curve defining them during electrochemical machining process. Now, in thermal machining process, material is removed from workpiece using. So all of these are actually can actually give rise to the temperature. The temperature may rise, and melting and evaporation can be the factors, okay, contributing to material removal. So light, plasma, and electrical discharge, all these processes are thermal processes in some way, and material can be removed using all these processes, right? So option D is the correct one here. And the last question was a numerical out of your alloy material removal in case of ECM. We have done that. You have to find out the equivalent density from the individual densities of all the components, and then you have to find the material removal rate using this particular formula. Okay, so so I hope you could have solved this problem too. and your average. First, you find your average density. Okay, so individual densities are given in this table. This particular density column you can see, and from that you find out the average density. Plug in the value of that in the equation for material removal. Okay, and you just transform your this value. Okay, so the fraction of the particular percentage composition of the particular individual components, okay, multiplied by your valency of the components, and you divide that by the atomic atomic weight. Okay? So once you do that, you get to your final answer as 0.041 centimeter cubes per second. Okay, I hope these problems are cool, and you could have done all of them. Considering so, we'll move to some concepts related to move to the discussion of some concepts, okay, related to EVM, electron beam machining, and laser beam machining processes. I know these are precision machining processes, and this will bring us towards the end of non-conventional machining processes, and then we'll discuss some of the basic introductory concepts from additive manufacturing, and some of the most important or most popular AM processes such as SLS, SLM, and DD if you have hard. And, that would conclude today's session. Okay. So moving on, let's start with this session. Okay. So let's start with the basic principle of electron beam machining process. Okay. So take a look at the pictogram towards the right of the slide. You can see a cathode grid, okay, which actually. So what exactly is the EBM process? It is a thermal machining process, right? To some extent. A stream of high-speed electrons actually are emitted from a cathode. You can see the cathode grid here. These electrons then travel at a high speed under a potential difference in the order of few hundred kilovolts. And when they strike the surface of a workpiece, they actually do erode a small portion of that. Okay, so that way EBM becomes suitable for drilling fine holes, right, and cutting some narrow cavities. Okay, so this is the actual basic principle. Now, if you look at this diagram, you can see that this cathode, which is a hot tungsten filament, actually from that cathode, it is a cup-shaped grid, which actually accelerates the electrons, shapes the electrons. Okay, it shapes the electron beam, and then the electrons are accelerated due to a large potential difference, okay, as I mentioned, in the order of a few hundred kilovolts between the cathode and the anode. Then the beam gets focused on the workpiece, okay, through the electromagnetic lenses. Okay, you can see here um, this magnetic lens being shown, the electromagnetic lenses which actually help in focusing the electron beam. Okay, and then these are deflection coils which are used to control the movement in any required direction. Okay, and then what happens is you have to maintain a high vacuum chamber, right? That is one of the necessities for EBM process, or you can say one of the constraints of EBM process. Now, moving ahead, what is the basic mechanism or mechanics of EBM machining? So let's suppose this is your material under consideration, okay? And uh, this is one electron beam incident on the surface. Now, for the first few, for the first little distance, just close to the surface of the material, the electron beam merely or hardly makes any impact. Okay, the material hardly realizes that an electron beam of consisting of high-speed electrons is intruded it. Okay, so this particular layer is called as a transparent beam transparent layer. Okay, this particular thickness is your beam transparent layer thickness. Then comes the actual depth of the material beneath that transparent layer, where you can actually see that the beam is interacting with the molecules inside the material or colliding with the molecules. Okay. Now, this is how the kinetic energy of the particular electron beam is reached after giving an acceleration voltage difference. Okay, it is half mass of the electrons multiplied by u square. U is your final velocity, not is initial velocity of the electrons. Okay. Now that way, final velocity becomes 600 root of the applied potential, and this is your potential difference. Okay. Now, this 600 takes care of this kinetic energy, in other words, the mass and velocity of the electrons and everything else. Okay. This is an empirical relationship, and then the fast moving electrons in beams on the work surface pass through this undisturbed or transparent beam transparent layer. This undisturbed layer is also called as beam transparent layer, okay, as you can see here. So after that, what happens is the electron starts colliding with the molecules inside the material, and ultimately they're brought to rest. Now, the collision of these electrons with the lattice atoms leads to loss of kinetic energy and hence generation of heat inside the material. Okay? So that's why it is also called as a thermal process. Electron beam emission is also called as a thermal process. Then the total range of penetration depth, that is the much the electron beam happens to enter inside the work material, is actually related to your applied potential difference and then your density of the material under consideration. So delta here gives your total range of penetration depth inside the material. Okay. Now, given that, uh, we can have a look at the temperature rise that happens in the work material. Okay, so this is your 1D heat equation. Okay, all of you must be acquainted with 1D heat equation from heat transfer process or thermodynamic processes. So now this is d theta dt is your temperature differential with respect to time. Alpha is your thermal diffusivity, and dou to theta dou z2 is your space variation of temperature. Okay, and then these are 1 by heat capacity C into rho density. Okay, and in the numerator you have H as a function of Z and T, where H you can see is the heat source intensity. Okay, heat source intensity. Z is the distance from the surface, or you can say the penetration depth, and theta is the temperature as said. So if you assume that the beam is a steady one, then T variable goes away, the time variable goes away, and the heat source intensity becomes your time invariable function. Okay, and is related then to Z as a exponential of minus of Bz. B denotes your energy absorption characteristic of the material. Okay, so what is B? B is your energy absorption characteristics of the material. Okay, so proceeding ahead, you find that the final equation or governing equation describing the surface heating during electron beam machining process, that is considering it is a time invariable, the heat intensity is a time invariable. It remains constant at time. Okay. Then you just replace this equation of heat intensity into the 1D heat equation problem, and you find that it varies in this way. This dou theta as a function of z and time, space and time, becomes your thermal diffusivity multiplied by dou to theta as a function of z, space and time, dou z2 plus A by rho C is a constant e to the power minus Bz. Okay? So as said, B is your energy absorption characteristics of the material. B defines your energy absorption characteristics of the material. So this is a typical theta to Z relation, which comes up from the solution of this 1D heat equation. You can see with time the temperature first rises and then decreases with space, okay, at different time constants, tau1, tau2, and tau3. Having said that, we go on and find out the parameters affecting the penetration depth of the beam. Okay. Now, this have been done using Buckingham Pi theorem. Okay, so dimensional analysis, all of you, I think, must have learned. You must know how to find out the dependence of certain variables on a particular parameter through Buckingham Pi theorem. Okay. So let's go and discuss it a bit. So here you can see that Z, which is the distance to which the beam enters into the particular material. Okay, so Z defines that distance, depth inside the material. So it is dependent upon P, your beam power, which is current multiplied by your accelerating voltage V. Small v, or you can say that is the velocity of the beam with respect to work, and then d is your beam dia, k is your thermal conductivity, and then rho and c are densities of specific heats respectively, and then theta m is your melting temperature. Okay. Now, in Buckingham Pi, you have to find out the number of basic dimensional units, and then you have to find out the number of dimensionless groups by subtracting the basic dimensions from the total number of parameters. So in this case, we have 1, 2, 3, 4, 5, and 6 and 7. We have, including Z, we have 7 parameters. Okay. And then from that, you have 4-dimensional basic units, okay, which are your which have to be subtracted from the total number of parameters 7 to find out the number of dimensionless groups. In this case, we found out these as 3. So pi 1, pi 2, and pi 3, 3 pi variables you should consider, right? Now, using that, we proceed you just write these all the parameters in terms of mass length and time coefficients. So the power varies as ml raised to the power 2 t raised to the power -3. That way K varies as ml t raised to the -3, temperature theta raised to the power -1. Velocity is your length per unit time, so L t power t raised to the power -1. Rho c is your heat capacity multiplied by your density. Okay, L raised to the power -1, t raised to the power -2, temperature raised to the power -1. Then your diameter is a length coefficient only, so L raised to the power 1, temperature theta, and the distance of penetration Z in terms of L only. Okay. Hope that is clear to you. Okay. Now, so you define your first pi variable as Z, and you take the 4 these are called as your basic dimensional units. Okay, so you take P, V, K, and rho c, your volumetric heat capacity. Okay, so rho multiplied density multiplied by your heat capacity C is called nothing but your volumetric heat capacity. Okay, so doing that, you you take the powers, that is the dimensions of variation as alpha, beta, gamma, and delta. Similarly, you take pi 2 and pi 3 and just proceed with the replacement of of the MLT powers, MLT constants of all these. Okay, to find out pi 1, okay, as your L multiplied by your what was that power, right? Force per unit time or energy per unit time. It is your ml power 2 t raised power minus 3 whole raised power alpha 1. Similarly, this is a velocity. Okay, this is your volumetric heat capacity, and this finally is your sorry. Yeah, this is your volumetric heat capacity, and this is your thermal conductivity K. Okay. So when you have replaced all of them, you just take the constants for pi 1 as m l p theta are 0, right? And you just compare all the values of m, l, and t for the right hand side and the left hand side, and you find out the value of the constants alpha, beta, gamma, and delta for pi 1. That way, after you place them in their respective places, you find the pi 1 variable as z v rho c upon k, and then the similar way you find pi 2 as dv rho c upon k. So that way you find pi 3 as k squared theta upon p rho cp. So now you get to find the final relationship. Pi 1 is a function of pi 2 and pi 3. And then you consider that your experimental results, which show that your Z, the depth of penetration, is generally proportional to the power P. And then this term Z K theta upon P generally varies as generally varies with respect to this dv rho c upon k to the power minus 0. Okay. So yeah, so where we were is that just you find out the values of pi 1, pi 2, pi 3, and use pi 1 as a function of pi 2 and pi 3. So this was your pi 1, this was your pi 2, and this was your pi 3. Okay. After finding out the constants alpha, beta, gamma, and delta for all the 4 variables, okay, and then you find out the net value of z, okay, by considering the experimental results. It says z is directly proportional to power p, and on this term z k theta upon p is proportional to 0.1 multiplied by dv rho c upon k raised to the power minus 0.5. So when you have done that, you find z as 0.1 p upon power upon theta and temperature multiplied by the square root of kdv rho c. Okay, rho c is your volumetric heat capacity. So the depth of variation, depth of penetration actually varies with all these particular parameters, and then you consider that we will go to some numericals, but I hope these things are clear to you. So let's proceed with the numericals. The first one asked you to determine the speed of cutting, given that you have a 150 microns wide slot, okay, in a 1 mm thick tungsten sheet, and then a electron beam has an intensity and a power of 5 kilowatt. Okay, so this relation we have discussed. P varies, power varies as a function of CQ. C is, for tungsten is 12 generally, and Q is your material removal rate. Okay, so 150 mm has been given as your slot width. Okay, you convert this is in microns. 150 you convert, okay, so after that you have to multiply it by your depth, 1 mm thick. Okay, and then your velocity in this whole thing has been taken in mm cube per minute. Okay, so you just take down, you just keep v as a variable here and just plug in the entire values in p equal to cq relation, and from that you can find out v as 4.6 centimeters per second. Okay, so this 1000 has been divided to convert these microns, okay, to mm here. So using all those things, you find out the final velocity in centimeters per second. Okay, you got it. So that said, the next question was about determination of the electron range, and in that case, your this kilovolt was your accelerating voltage, 150 kilovolts, and then you have to find the electron. That's a simple relation. We had discussed it in our earlier slides. And the penetration range, okay, delta is given by 2.6 to 10 to the power minus 17. This is an empirical relationship, of course, multiplied by your v square upon rho. So your v is the accelerating voltage, which is given as 150 kilovolts. You convert it to volts, and then you divide that by density of the particular material. This is steel workpiece, and this is the density of steel, and then you find out the electron range as 77 microns. Okay, I hope that is clear too. So given that, we move to the last problem from electron beam machining. we had just done the dimensional analysis problem to find out the parameters or factors which directly or indirectly affect the depth of penetration of the electron beam inside the workpiece. And this was the final relation I found, and these are the particular parameters. Now, this question asked you to find out the speed of cutting. Okay, so you have to find out this velocity v. Now, power rate is given here. Okay, and then the temperature to which the temperature, melting temperature. Okay, for this tungsten. You can take that from the earlier problem. Okay, that was 3400 degrees centigrades. Okay, and then there are your thermal conductivity, and then D is your dia of the slot, right? And then v is your velocity, which is unknown. Rho is the density of this whole thing. Rho c is the volumetric rate capacity. Okay, so you just plug in all the values and then you find out the velocity is 24.7 centimeters per second. Okay, hope this clear to you. So in this problem, if you're wondering, volumetric heat capacity for tungsten rho c has been taken as 2.71 joules per centimeter cube. Okay, and then the temperature theta m, sorry. So the temperature is theta m for tungsten, which is 3400 degrees centigrade. Okay, and then thermal conductivity K for tungsten is again 2.15 watt per centimeters degree centigrade. So now this this has been given to you, dia of the slot to be cut, velocity you have to find out. 2.71 is your dose value. Okay, 5,000 is your watts power. This is a constant. This is 1 thick sheet which is given to you. Okay, now this is actually, you can say, depth z. Okay, so considering all these things, you finally find the velocity is 24.7 centimeters per second. Okay, now it's clear, I guess. Considering that, we'll start a new topic of laser beam machining, starting with the basic principle of laser beam. Okay, now you know that laser beam machining is also a kind of thermal process, and mainly the principle by which laser is generated is uh, is known to all of you. To recap, I would mention once that suppose a laser, what it does is once a particular molecule is excited to a higher energy state by taking up one photon, and then when it comes back to its initial state, it releases one photon. Okay. So this is then two types. This release is then two types. One is the cascading effect. The one photon releases to cascading effect of the same particular molecule, and the other is that when it just excites another molecule at that particular energy level. Okay, so when that does, that is again causes a higher intensity of release of photons. Okay, so that we pick up and concentrate on a particular workpiece through some optical systems to finally do some melting and high-speed ablation on the workpiece surface. Okay. Now, I hope then I can continue the LBM process really. Okay. So you can have a look at the diagram, the schematic representation of the aluminum process on the right hand side of the slide. So you have a Ruby laser setup, pulse Ruby laser, which is a typical laser system. Now there is a Ruby crystal at the center. You can see that this is a Ruby crystal at the center, and we have a xenon lamp or a xenon flash tube which can coil around the entire Ruby crystal at the center. Okay. The xenon lamp consists of a highly reflecting internal surface. Okay, and it is made of highly reflecting material, so that the maximum light falls on the ruby rod at the center. Okay, for pumping operation. By pumping operation, you mean that exciting the electrons to higher energy levels, and then when they come back to their initial state, the release of photons. Okay, that is actually called as population inversion phenomenon, right? Now, so that way, what happens is there is one lens which just converges them on the workpiece and leading to the material removal, right? Now the capacitor is charged and a very high voltage is applied to the triggering electrode for initiation of the flash. Okay? Then the emitted laser beam then is focused by the optic system, as I said before, and the focused laser beam removes a small portion of material by vaporization and high-speed ablation from the work surface. Okay, now this uh, on this material, this removal of the small material chunk from the surface of the workpiece is so fast and so quick that a substantial mechanical response impulse is generated inside the work, and then this leads to a large amount of surrounding molten material to be thrown out, okay, or spattered. Okay? You know the term spattering from welding processes too, right? Now, once that is actually the phenomenon in case of laser beam machining process. Now, broadly, it involves interaction of laser beam with the work material, okay, heat conduction and temperature rise at the workpiece surface, and then melting, vaporization, and ablation. Okay, so this particular figure actually explains how the intensity builds up. Okay, so with the increasing depth of the inside the work material, the intensity varies as suppose Z at a particular depth Z. The intensity varies as the initial intensity multiplied by exponential of minus of mu Z. Okay, mu be a constant. So that way, the intensity varies exponentially down the negative of exponential with the increase in depth inside the work material. Okay, so a part of the incident light may also get reflected. Of course, you know that. Now, that is the basic phenomenon of laser beam machining. Okay. Now, we can similarly, we can also look to the temperature rise in case of LBM2. However, this needs some assumptions such as the conduction, the heat conduction that we also consider in EVM. Then dia of beam be larger than depth of penetration be Z, and dia of beam be D should be larger than Z. Okay. So then thermal properties remain unaffected okay, with temperature change. Actually, that doesn't happen. But to derive these temperature rises inside the workpiece, which is a highly complex phenomenon, we have to make some assumptions. So this is one of them, that the thermal properties remain unaltered with the increasing temperature. Okay, and uniform heat flux H at the surface of a semi-infinite body. So the heat flux also remains uniform throughout the operation. That is a fourth assumption here. And the body be semi-infinite body, the surface at which we are focusing the laser beam. Okay, let us consider that the semi-infinite. Considering that, to just pick in the heat conduction equation with alpha being the thermal diffusivity and theta as temperature, similar to what we have done in electron beam machining. And then you just use the initial and boundary conditions to arrive to the expression for theta as a function of space and time as 1 by k thermal conductivity square root of alpha upon pi, and then the integration of h, okay, which is your heat intensity multiplied by T minus your constant tau divided by the tau exponential of minus of z square by 4 alpha tau to tau. Okay. So said that you assume the laser beam pulse to be a step function okay, where heat flux H remains constant. Then you can modify this equation 1 and as 2, okay, where you plug in, you chip in the error function cosine of error function C value. Okay. These equations, derivation of these equations follow complex methods, complex steps, which I don't want to mention here. but you should at least realize the how with different parameters the temperature rise can vary. Okay, that's very important in this case. Uh, okay. So if you have got that, so you can see that the surface temperature theta m at by surface temperature will mean that your z becomes 0, isn't it? Your z becomes 0, then your surface temperature becomes 2h by k alpha t by pi to the power half. Okay, and from that equation you can deduce your time for time reach the melting temperature as pi by alpha theta m conductivity by 2 of heat intensity whole square. Okay, so these equations are quite important, and if you have got them, we'll move to a more realistic approach to consider, which is actually to consider a circular spot with the die equal to that of the focused beam. Okay, so if you consider that, then the expression for your temperature with respect to space and time gets modified to this, and your surface temperature gets modified to this equation, where this is the ERFC is the imaginary error function of part of error function of sine cosine of error function value with a function of d by argument of d by 4 to the alpha. Okay, so given that, yeah, um, so given that, we'll proceed to find out the value for a high large duration time. Okay, when the duration is t is much larger, then your theta m reduces to 2h by k to d by 4 1 minus a function of d by 4 dot alpha tm. Okay, tm is your melting time t. Okay, then from that you can find out the tm, or you can find out the temperature at the end of time t. Okay, now this is the H critical value. Okay, the minimum heat intensity which should be required to find that melting temperature. Okay, so this can also be asked to you in your paper, and then you have a steady state hole penetration case that is happens when rate of heat input becomes equal to your rate of heat loss by the side walls of the molten pit. Okay, in that case, and this is the energy balance equation, which you can note. Okay, so having recapitulated all these particular equations in case of laser beam machining process, we will then move to some numerical problems. Okay. Yeah, so before that, from that energy balance, you derive this approximate height of pit which you can achieve. And this is the simplistic version of the heat input rate to vaporize the material, given that you are given the velocity which at which surface recedes and the amount of energy to vaporize unit volume of material. Okay. So this is for very high beam density. So these are certain heat generation temperature rise equations. One at generalized case, which we have found these equations. Okay, then you find something a modified version when you take that temperature at the surface. Okay, and then you take a generalized circular spot of beam with a dia equal to that of the focused beam. Okay, the heat flux to be active on that circular spot only. And then one generalization is when time is very large, exposure time is very large, and the other case is when the beam intensity is very high. Okay, so all these are certain conditions which may arise in case of laser beam machining. Okay, so given all these things, we'll move to some problems out of laser beam machining. Yeah. So this problem actually has asked you to find out the time required for the surface to reach melting temperature, given that all these things. Okay, your laser beam power intensity, your melting temperature, thermal conductivity, and volumetric heat capacity. Okay. And specifically, they have asked that 10% of the beam has to be considered to be absorbed. Okay, a lot of the energy gets wasted actually. So this is how you solve this kind of problems, as we have discussed earlier, right? So we have discussed here the time to reach the melting temperature theta m, considering the penetration as z as 0. Okay, so you find that Tm is pi by alpha theta m k by 2h squared. Okay, and where you just plug in all these values. Alpha is thermal diffusivity k by rho c. You plug in the values of k and rho c. You find the heat intensity. Okay, using the given variables, which are your 0.1% they have told you to use, right? I mean 0.1, that is 10%, right? So 0.1 of the total power intensity given to you, that is 10 to the power 5, right? This becomes your total intensity. Then you just plug in all the values to the equation to find time to reach the melting temperature, and then you can find it to be very small time, as almost equal to 0.53 milliseconds. Okay, I hope that is clear. So, yeah, I hope it is clear. Then we proceed to the next question, in which the data is exactly same. We just have to consider a circular spot here and find out the time to reach the melting temperature. However, in this case, you have to take care of this Xi value. Okay. Now, we had earlier discussed that in case of probably electro-discharge machining, right? That how do you solve this kind of problems? So you have to just equate both the LHS and the RHS side. Okay, you just have to equate both the LHS and RHS side and see that for what value of this argument and corresponding imaginary error function value to error function value, the both the sides becomes equal. Okay, from that you take up the argument value corresponding to that particular imaginary error function value, and then you just find out the unknown variable, right? So in this case, so Xi is nothing but your d by, right, 4 root of alpha t. Okay. So we have found that for a value of 0.5, for a value of Xi equal to 0.5, these LHS and RHS becomes equivalent. Okay. So from that we find out the value of Tm, putting Xi equal to d by 4 root alpha t. So here you don't get confused with beta. Beta has been just used to make the equation seem simpler. The square root of 179t Tm has been replaced as beta here. So ultimately you have to find the Xi value. Xi is the argument of the imaginary error function, right? So you have to find out the Xi value and the corresponding imaginary error function value, for which the whole expression on the right hand side comes down to 3400, right? And then that particular Xi value you have to equate to find out the unknown value of time t. I hope that is clear, right? Otherwise, these are simple formulations. There is nothing to stress about. And then we move to the next problem. It is a simple problem. You have to find out the minimum value of beam power intensity to achieve the melting. Okay, in case of laser beam machining, we just found that out. Its critical happens to be your 2k theta by d. So just plug in all the values of the variables k, theta, and t. You can use that as similar to our previous problem values, and find out the critical heat intensity becomes 7.31 10 raised to the power 6 watt per centimeter square. Okay. Now, I hope solving and understanding this kind of problems covers most of the topics out of your laser beam and electron beam machining processes. And given that, this is a simple last problem, after which we move to some concepts of additive manufacturing. So here you have to find out the time to drill a hole, but this is here you can see that it is a very high power intensity. Okay, so for high power intensity, we have used this kind of relations, B equal to H by L. That a very simplistic version. So you just plug in the value of H, which is 10% of whatever given to you as the laser beam power intensity, and then multiply it by L, which is the energy required to vaporize of the latent heat. Okay, which is 3 into 10 raised to the power of 4 joule per centimeter cube. Okay, so when you have done that, you find out your time coming to be 0.0015 seconds. Okay. So here by this problem, we almost conclude our EBM and LBM thing today, and now we'll move to some concepts related to additive manufacturing process. Okay. So, what exactly is additive manufacturing? As most of you have heard about 3D printing and additive manufacturing related concepts. So, additive manufacturing is actually related to making objects layer by layer from 3D CAD data. Okay. So different from material removal, it is different from material removal in traditional subtractive manufacturing processes. The 3D CAD model you first design in some CAD software such as AutoCAD or SolidWorks or CATIA, right? And then you convert it, you save it as an stl.stl file, you slice the layers, okay, and set the tool path. Okay, and then just deposit the material layer by layer to finally develop on the 3D object. Okay, so that is why, since you are not removing any material and just depositing layers of materials over one another, so that's why it becomes an additive manufacturing process. You're adding layers of material over one already placed layer. Okay, so that's how additive manufacturing has got its name. Now, what you see is what you build process, right? Because you can technically build anything you want depending upon the design you make in your software, right? So digital 3D design data is used to build up a component and layers by depositing material. Okay, and this is a bottom-up process. You have a layer by layer build up, right? So that is actually additive manufacturing, right? I hope you got that. So then we move to the next topic, as in why exactly additive manufacturing. Okay. So you have several benefits. Okay, so firstly, additive manufacturing gives you products which are highly efficient in material consumption. Okay, so wastage of material is very low because you don't have to remove materials. Okay, you are just adding whatever amount you need. That's it. You don't have to do post machining processes to give rise to your final product. Okay, energy consumption is very low. Then tooling reduction is reduced because a single machine can do a lot of different structures. Okay. Then time to market inventory reduction is there because you don't need a lot of things to develop a particular product. Okay, and then if you can make in a shorter period of time, then the equipments are equipment requirements are small or very low, then the time to market inventory time to market inventory reduction is highly shortened, right? So you can see the type of this type of toolings and dies can be manufactured through additive manufacturing at concept levels, right? Then it says in geometry and material complexity is not an issue. You can technically give rise to any the level of complexities. Okay, you can actually manufacture any types of any level of complexities to in processes, such as a complex heat exchanger, a hydraulic component with internal geometries, a conformal cooling equipments, okay. And then the product optimization by applying innovative design concepts, okay, because you can reduce material consumption by redesigning the material through reduction of weights. Okay, if you have noticed some chairs in which you don't have the whole solid structure and rather this type of meshed structures. Okay, this type of mesh structures. So that is actually called a freedom of design. Okay, and it leads to manufacturing for design concept. Okay? In all these cases, you can see there's a lot of material reduction. Okay? You only use the amount you need, or you can reduce the weight, you can reduce the material wastage. So you can suitably use them as for functionally graded materials. Okay, hybrid manufacturing can also complement or that is, I mean, you can use it in conjugation with conventional manufacturing processes. Okay? So in case of biomedical implants, also 3D printing is now additive manufacturing is now being widely explored. So here is a differentiation between CNC and additive manufacturing processes. So in case of CNC, you need some manual specific codes, but these are not actually needed in case of additive manufacturing. Okay. So you know these G codes, M codes, and all these are not actually needed in additive manufacturing. Then you have a very difficult for complex part geometry. Okay? They can additive can actually give rise to complex geometries in a layer by layer manner easily. Okay? And this is, you know, is a subtractive process. An additive process, material wastage is almost not there in case of additive. Then you have a homogeneous properties achieved in case of CNC machining, but there can be foils or anisotropy in case of editing. Okay, so that is one disadvantage of additive manufacturing. And then multiple tools are needed there, but tooling requirements are almost a lot minimized in case of additive manufacturing, right? Working principle is always metal cutting, and here you use metal addition. Okay, and this can be different for different AM processes. So the application are wide, starting from aerospace to biomedical to edit automotive to prototyping to jewelry to architecture. Okay. And even satellite and components have been manufactured additive these days. And bioimplants, of course, these are widely explored in the case of bioimplant manufacturing. Okay. So it is on a surge now, and in the next 10 years, is expected to reach at the household level, okay, manufacturing processes. So here we have a simple, here we have a detailed classification of the additive manufacturing technology. And this can be classified based on your processes, your material, uh, used, and then the deposition mechanism and the energy used, right? So depending upon the processes, there can be extrusion, as in case of FPM, there can be polymerization, in case of DLP, sintering or melting. Okay. In case of SLM or SLS, then ultrasonic metal fusion. Okay. Now, under the hood of material considered, it can be polymer, metal, cellulose, ceramics, and resin. Though currently polymer processing for additive manufacturing are have been widely explored. The exploration for metals and alloys, ceramics, and resins is also underway, and a lot of research are being carried out. Okay. Then deposition, depending upon the deposition method. Sorry for the disruption. I got disconnected actually. So we were here, and then we were discussing the classification of AM technology based on energy used. We may have laser based AM processors is in SLM. Okay, we may have electron beam based electron beam based AM technologies is in EBM. We may have ultrasonic vibration based technology. We may have infrared radiation based technology. We may have ultraviolet radiation based technology as in DLP processing. Okay. So after that, we have we will discuss 2 to 3 types of AM technologies in details, right? So the first one is about selective laser sintering. As you can see in the diagram, you have you have a table or a bed on which powders are pre-placed, okay, powder bed, and then you just scan in a layer-wise manner. Once you scan a particular layer through the laser beam, the actually one unit of thickness you lower the piston, okay. The powder delivery piston, you just bring it down by 1 unit of thickness, and once that is done, you actually place the other layer and scan it again to get the second layer done. Okay? So this is the way in which selective laser sintering actually works. So to go in detail, the process works by using unlocalized heat from laser to selectively fuse the powder material, right? Often by sintering or melting. So what's the difference between sintering? Sintering is bond formation prior to melting, right? So that is called a sintering. So based on that, you have SLS method, selective laser sintering. The powder is not completely melted here, and bonding happens prior to melting temperature is reached, right? So the sintering, often by sintering or melting of the particles or melting of a binder applied to a powder particle. It's okay. Typically, either a continuous wave or a modulated CO2 laser is used with power ranging from 1 to 250 watts. However, currently Nd:YAG and fiber lasers are also being used. Now, if you don't know, then fiber lasers are solid state lasers, and CO2 lasers are gaseous gas lasers, and Nd:YAG is based on crystal. Okay. Uh, Now, Nd:YAG and fiber lasers produce much higher powers as compared to CO2 lasers, but the issue is they are highly expensive in nature. Okay? However, you can get very low wavelengths around 1 microns in case of both Nd:YAG and fiber lasers. However, in fiber lasers happen to be the most expensive ones, and you can get very high resolution and a very small spot radius actually. So, uh, proceeding, you have the working principle of selective laser sintering process. So a layer of powder is spread typically 0.1 millimeters thick over the elevator or the piston you have seen there, right? Inside the chamber. Okay. So this has been called as the elevator. You drop in the powder, so powder layer. Yeah. So a layer of powder is spread over the elevator and pressed. Okay, each layer of powder is preheated before the scanning to minimize the heat input from the laser. Okay, and then preheating. Why that is done? Preheating of powder does generate uniform temperature within the build platform and prevent warping of the part during build due to non-uniform thermal expansion and contraction. Right. So just take a note of this point. What is the requirement of preheating before after each powder layer has been spread, right? And then you have the laser radiation then sinters the powder to form the profile. Laser radiation then sinters the powder to form the profile of the section. Okay. To form the profile of the section. Now the elevator then drops or comes down by a distance equivalent to the desired thickness of the section, and the process is repeated until the prototype is completed. Okay. So that is the working principle of selective laser sintering method of M technology. And then the nitrogen atmosphere has to be maintained in the fabrication chamber to prevent the possibility of explosion in the handling of large quantities of powder. Okay? And then to increase the density, we use hot isostatic pressing as the post-processing of the additively manufactured product. So, okay, so given that, yeah, and the powders which remain loose around the product serve as actual support for the subsequent layers, right? Thus eliminating the need for the secondary supports which are necessary for photopolymer wet processes. Yeah. So after that, we have some advantages and disadvantages. So any powder which can be sintered or bond without melting can be used. And also that doesn't require additional support structures as we discussed in the earlier slide. The unbonded or loose powders indeed offer the support to the product, right? Then these are high accuracy processes. Then we have a full, you can have a fully automatic process in SLS. These are and you can also make large parts, okay, large size products. Now, considering that there are disadvantages too. Such as you can't make large flat sheets which needs tie down supports to stop curling. Okay? And if you need additional supports for large sheets, then surface finish is rough compared with that produced by the stereolithography processes. Yeah, and then yeah, expensive the equipment, so the initial expenses are high as the equipment happens to be expensive, then temperature control becomes critical and the equipment size is highly large, is quite large. Okay, so these are your major problems and related to your SLS process. And then the next one you have is selective laser melting, and the process is pretty much similar, but the powder is actually melted in this case. So full melting of the particles, and then you have your resolidification. Okay. Then SLM produces powders with much higher density and strength because the particles are actually melted and can process metals, alloys, and MMCs, metal matrix composites like stainless steel, tool steel, cobalt, chrome, titanium, etc. So there is a wide range of metals also which can be manufactured, which can be processed through SLM process. Now, looking at the process, the heat generated causes the powder particles to melt and form a melt pool which solidifies as a consolidated layer of material. Okay? Now, as you said, SLM is very much similar to SLS in terms of equipment because both uses, but both uses a similar kind of strategy through that piston, or you can say through that elevator thing that we discussed earlier. So both uses that to smear, take one layer of powder and then dropping down by a unit thickness and then record thickness and then spreading the second layer over the earlier one. Okay. But in case of SLM, the only difference is that the equipment uses a much higher energy density, right? Because you have to have a full melting of the powders. Okay? Therefore, the fabricated parts exhibit a very high density, which is close to the theoretical one, whereas the densities are quite compromised in case of sintering process. Yeah. And now, given that, we have the advantages and disadvantages of SLM process too. So complete melting of powder in SLM means that you have higher strength and density of the product. Okay, negligible waste of material because the unused powders can also be recycled. Okay. And then you have the possibility of producing a complicated shape. For example, you can have a steel mold with curved internal cooling channels. Yeah, that is quite complex structure that can be made through other end process too in general. Okay, and then here no distinct binders or melt freezes are required because the powder itself is getting melted, right? You don't need additional melt freezers or binders, right? And you have unique properties. You can get unique properties and that are distinct and sometimes more desirable. Okay. Um, so these are the advantages. However, the disadvantages are related to the imperfections such as low quality down facing surfaces. Okay, then greater upper surface roughness and the risk of internal pores. So all these are issues related to this selectiveness and melting process. And then often you get a coarse grainy surface which gets be machined. So so post processing again adds up to your total machining time. Yeah. And then high temperature gradients. There are high temperature gradients in case of SLM because complete melting of powders is being carried out. This may increase the risk of delamination and distortion due to large thermal or residual stresses. Okay. So large stresses may develop, which can lead to cracking or delamination or distortion at minimum. Okay. So these are the issues leading to this SLM process, okay, of AIM technology. And then we'll take down one more commonly or most highly being used in the aerospace industries these days. You have the direct energy deposition process, in which you don't actually spray the powder first and then melt it or expose it or scan it to the laser beam. Rather, you do it simultaneously. Okay, as you can see in this diagram. So going to the steps that you first slice the solid model is sliced electronically into a sequence of layers of a given thickness. Okay, and then to build the metallic part, what you do is the solid substrate is used as a base, and the laser beam is really focused on the substrate to create a molten pool into which powder is being simultaneously fed. Okay. Now the substrate is then moved beneath the laser beam, tracing the pattern. Melting material is added to the surface as a narrow strip of added material. Okay, so it is happening simultaneously. So starting from the bottom of the pot, one layer is being produced at a time, and after formation of a layer, the powder feeding nozzle and the laser beam assembly is then moved in the set direction. So that way, the second layer gets built, and the process of layer by layer deposition gets completed to give you the final part. So the machine actually employs powder delivery through a nozzle placed above the part, and the powder is melted where the material converges with the laser and the substrate. And so there is no pre-spreading of powder over the bed. Okay. And then you have the advantages and disadvantages of this direct energy deposition process of AM technology. So the main advantage here is that you can get highly dense structures. Okay, and then you can produce gradient materials by applying different powder delivery nozzles, isn't it? So because the powder is being melted simultaneously, where the beam converges with the powder supply, right? So you can produce gradient materials here. Then uh, you have the capability of selectively applying metal to existing parts, or then repairing worn or broken parts while maintaining the integrity of the parent material, right? Okay, so as initially said, can get highly dense and corrosion resistant as well as wire resistant metals. Okay, so you can have high performance and lifetime of the components achieved. You can look at the biomedical implants, for example, right? And then regarding disadvantages, you have very few materials which can be processed through this technique. You have a large unit size, you have high power consumption, so that makes it highly expensive again. And the main limitations are resolution and surface finish. So although you can again get dense structures, you can get radiant materials, you can actually have high performance, but the resolution and surface finish are poor in that case. So slower build speed again adds up to your total machining time, total manufacturing time. Okay, and when you just compare it with the other additive manufacturing processes, not much complex structures can be developed, okay, as in PBF processes or powder bed fusion processes, because support structures are needed and multiple axis deposition are needed for complex geometries. So that is a major issue in case of and direct energy deposition processes, right? So that pretty much concludes today's session. I know we have taken up a lot of content today. Now, if you have any doubt, you can please ask, because we still have 5 to 10 minutes left for today. Next session will be our last one, and probably will summarize the entire course once and just take up some of the topics which have not been covered throughout in the next session. So given that, so that concludes today's session. I'll be still be there for some time to address some of your doubts if you have.